All right, so it's 10 and we should probably start. Thank you. So welcome to this session of DIVE this morning. DIVE essentially was started to focus on the area of design, thinking and innovation. Broader area is design, and design is not of everyday stuff, but we are now going to the level of cosmos, design of cosmos. Essentially, it is about wondering things around us, figuring out some cues, what we can do to keep our creative juices flowing, and figure out how to shape our lives better, shape our environment better, shape our things around us better. So we've done several sessions. Last session was around genetics. Prior to that, we were discussing sustainability. And this time we have more exotic topic, astrophysics, trying to figure out what lies beyond the stars and how do we go there. But why do we really go beyond the stars at all? Any thoughts? Why do we really focus on the sky and try to look for something? What? Any idea?
Innate curiosity.
Curiosity. We want to figure out sometimes what lies beyond. And by looking beyond, we will try to figure out who we are. Finally, the big question is also that where did we come from? I think the bigger question we are trying to solve also. And I think technology has gone a long way in figuring those questions out. One of the very interesting science is astrophysics, the radio physics in fact. And Dr. Yashwant Gupta here with us is a champion of the field, highly decorated scientist with National Center of Radio Astronomy. He's a Bhatnagar Award winner. In case you probably may not know, Bhatnagar Award is one of the highest scientist award, or in fact the highest scientist award in science in India. So we are happy to have Dr. Gupta with us. He takes us on the journey of the cosmos and the related changes which human mind is trying to explore in different facets of science. Rocket sciences are known to be spurring a lot of innovations by themselves, and we have a lot of interesting anecdotes also with his experience on this radio as well as the experiment what he's doing at the place close by Narayana, where we have one of the largest radio arrays here. So welcome again, and we'll keep it for 1 hour, half an hour of interaction, 1.5 hours is the overall time. We'll keep, I think it's up to Ken to keep interacting with you with the content. So it's a rich content and an exciting journey, and two important things. The rest room is right here, in case somebody wants to have water, right here. And we'll have tea and snacks in the end. Over to you.
Thank you, Manoj, and very good morning to all of you. Manoj and I have been talking about this for quite some time to try and make this happen. So I'm really glad that finally it has materialized, and it gives me a chance to talk to you all about some things which I think are different, and I think we all grow up wanting to know what is astronomy, what are the stars, and I think everybody has a little bit of a touch with it. But what really happens and what we do is a whole different deep field in its own. So we will take a deep dive into it. And one of the aims here for me is to give you a sense of what we do, give you a sense of what is our place in the universe, and in the process to highlight that what we do has a very strong interplay with technology. I mean, there's something we may not think about. We think of an astronomer with this guy with his telescope sitting and looking at the universe and learning things, but you will see that there is a tremendous interplay between astronomy and technology, and part of my aim will be to bring that out. So in some sense, this will be a journey. It will be somewhat meandering. Some of the meandering will happen for me as I go off in different directions but come back. But some of that I expect to happen from you all. So please interrupt whenever you want to ask something. We'll take a detour, address what you're asking, and then try to come back onto the track. Okay, so let's start. I'll just give first a bit of background and historical perspective. So, this thing that we call the universe or the cosmos, and you can ask what's the best way to study about it. Of course, some of the ancient rishis would tell you that you can sit with your eyes closed and learn all about it. But finally, when it comes to gathering data, we do it via astronomy, and it is therefore one of the oldest sciences. So once man learned how to become so-called civilized, settle down, have a steady life, then it is this curiosity that took over to see, look up and say, hey, what's up there? And what are these objects? What happens? And so on. So it started, of course, with the use of the naked eyes, because that is our natural detector for detecting light. And so, and that information that is gathered was processed by the human brain. So those were the tools, right, in the early days. And you'll be surprised that with those tools, coupled with, of course, logic, deduction, and evolution of mathematics, there was an amazing amount that was learned just with this much. And this is something that I think we hear about it, but this is something that we should understand. A lot of that, of course, happened in countries like India and China, where the ancients, just with their powers of observing with their eyes and analyzing, came up with amazing deductions. So, and I won't go into the detail, but we all hear about Aryabhat. And so we are talking, 5th, 6th century AD. So that's more than 1,000 years before the people in the West concluded these kind of things, that the earth is round, that it rotates on its axis, and it revolves around the sun. So this heliocentric model, which came up much later in the West, was something that was deduced based on just the ability to observe and analyze what was seen. So that's how it all started. But at some point, there was a big revolution, and that is when the optical telescope was invented. This was by one gentleman called Lippershey in Holland. But it was this gentleman, Galileo Galilei, who turned that instrument. Everybody was using it to look at objects on the earth. And he said, what the heck, I'm going to go turn it to the sky and see what I see. And that completely revolutionized observational astronomy in the sense of what you could see, what information you could get. There was a quantum jump. And it's interesting to just have a look at how the optical telescopes evolved. So this is Galileo's very modest, few centimeter wide aperture telescope. From then to Newton's time, and then William Herschel, and then you can see these bigger and bigger telescopes, and some of the ones that are now under construction are giant structures. So here the mirror is 30 meters in diameter. Okay, that's much bigger than the size of this room, for example. And so and then now you can start to see the interplay of technology. This kind of stuff requires some of the most modern technologies to implement and make it work, not to mention what you do with the huge amount of data that it collects. So we'll come back to that. But obviously, when you say there's a clear trend here, which is that bigger is better. For some reason, these guys are building these bigger and bigger telescopes. So you would ask why? What are they gaining by building these bigger and bigger instruments? Okay, that's a simple question. And there are two simple answers to that. One of which will be obvious to you. So when you go into a dark room, your pupils dilate, you open your aperture wide so that you can collect more of the light because you're in a dark environment, right? So the bigger the aperture that you have, the more light the aperture collects. More light you collect, fainter objects you can see, right? So this is what is called sensitivity, right? So when our eyes are more sensitive to the dark, we are trying to collect as much signal as we can, so that we can see the faint objects. So if you want to see the fainter objects, and in general, fainter means further away, by and large, not always. So you know that if you take a bulb and take it further and further away, it will become fainter and fainter, the light from it. So if you can see fainter objects, then you're likely seeing objects further in the universe. And when you couple that with one other simple fact, which is now well established, that light travels at a finite speed, right? We all have learned that. And so, which means that when the light starts from a certain object, it takes a certain amount of time to reach us. So when you see that light, you are seeing the object as it existed a little bit in the past. For us, it doesn't matter. We are talking about nanoseconds or picoseconds between us. But the moment you go to the moon, so light coming, bouncing from the moon and coming to us is already 2 seconds old. Light coming from the sun is 8.5 minutes old. So that means when you see a picture of the sun now live, it is how it existed 8.5 minutes ago. And sun is a relatively nearby object. When we talk about distances in astronomy, we measure them in units of how long light takes to travel. So an object which is 1 light year away is at a distance that light would take 1 year to cover. Okay. So now you say, okay, are there objects 1 light year away? Well, we know of objects which are millions of light years away, billions of light years away. Okay. So, so the moment you can detect fainter objects, you are seeing objects further back in the universe. Therefore, you can actually trace the history of the universe. So if you can see the sun as it existed 8.5 minutes ago, if you see a nearby star, it is 4 light years. So you are seeing the universe in sort of like flashback, that how it existed earlier and earlier in time. So that is why sensitivity is important, and that's why you want to build the bigger and bigger telescopes. The other one that is important is again something we all know. All of you who've used binoculars, you know that a binocular, you use it to magnify. What is magnification? Magnification is the ability that something which was not very clear to you becomes very clear in sense of spatial separation. So if two objects are nearby and you cannot make them out, then you use a binocular, you can see them as two separate objects. So that is called magnification. In our technical term, we call it resolution. So resolution, to ability to resolve objects which are otherwise merged and see them as distinct objects, which means you can see more detail about anything in the universe that you're looking at. So you would like to see that, right? If I am looking at somebody's face far away, if I want to know what the details are, I'd like to see that with higher resolution. And resolution depends again on the size of the telescope, on the aperture. The bigger the aperture you have, the better resolution you get. So sensitivity, as you can imagine, if it depends on how much light you collect, it should depend on the area that the aperture offers. And so if the aperture has a size d in diameter, then that area is proportional to d square, as we all know. So the sensitivity goes as the square of the diameter of the telescope. The resolution goes inversely as the diameter. So smaller resolution means smaller angles in the sky that you are able to separate and see. And so the bigger the aperture, the better is the resolution. The thing to remember is the resolution, because of physics principles, also depends on the wavelength of the light that is involved. So the lambda is the wavelength. So if the wavelength is different, then for the same aperture, the resolution will change. And this we will see becomes very important when we look at wavelengths across the electromagnetic spectrum. So I'll illustrate this with a couple of examples. So when we look at the moon with our naked eyes, we see a picture like this, right? You can sort of make out some details. When you start looking at it with the different size optical telescopes, you start seeing images like this. So now you can see the meaning of resolution, right? Now you're able to separate out, you can make out these different detailed features on the surface of the moon. And the same happens, I'll show you one more example. Any of you who dabble in amateur astronomy would have heard about the Andromeda galaxy, or even otherwise you would have heard about it. It is the nearest neighbor to our galaxy, other than our Magellanic Clouds, which are our satellite galaxies going around the Milky Way. So it is located in the constellation Andromeda. If you go out in a place where the sky is clear and the seeing is good, which means far away from city lights, then you will see a small hazy patch like this with the naked eyes. And then you start looking at it with bigger and bigger optical telescopes, you will see images like this. So here now you can see both fainter objects which were otherwise not visible start becoming visible, whether they are background other stars in our galaxy or features of the galaxy itself. So you're getting higher sensitivity, and you can start seeing the details of the shape of the galaxy, the features. So that is the resolution, right? So this is the reason why we build these bigger and bigger telescopes, which of course have their own challenges as to how to build them and how to use them. Okay, now we can ask, you're talking about light, and I think all of us have learned that light is just one narrow piece of a huge electromagnetic spectrum, right, which goes all the way from the very low frequency radio waves to the highest frequency gamma rays, right? So this is all stuff that we learn in school, and so when you see the electromagnetic spectrum, and the light visible part is a small piece here. Obviously, you will ask this question that if I see the galaxy in visible, is the galaxy shining in ultraviolet? Is it emitting radio waves? And if so, is there something that I can learn by if I could study the galaxy in these other wavelengths? Okay, so that is what then brings us to this question, which is that can I see the same object, whether it is a nebula or a galaxy or a star or a planet, in different parts of the electromagnetic spectrum? If yes, do I learn something different about it by studying it in the different wavelengths? And the third one, which is also very interesting, is are there objects or phenomena which don't emit light but could be emitting radio waves or X-rays? Therefore, if I had access only to light, I would never learn about the existence of those objects, right? So that is actually the answers to all of these questions is yes. And the one way I'll just explain this is, if you look at anybody, me, this is what you will see in an optical picture, okay? But if you were to look at me in infrared, this is what you will see, okay? And if you were to pass X-rays through me, this is what you will see, okay? So this is the point, and this is what your doctor does now. When you go, you say, I'm not well, he will say, I want to do an ultrasound, I want to do an MRI, I want to do this and that, and you say, why are you doing all this? That is because they are wanting to study in different ways and then combine that information to make the best diagnosis. Okay, and this is where we would want to go, whereby you can combine the information from different wavelengths if that object is emitting those wavelengths and come to the best possible physical picture of the object or the phenomena that we are studying in the universe, right? So this, I'll come back to this example. So we are back to our favorite of today, the Andromeda galaxy. So this was the optical picture that I showed you, and these are images assembled in radio, infrared, ultraviolet and X-rays, different parts of the electromagnetic spectrum, and how these got assembled will come back. So when I finish this diversion, and now you can see that point that just like your doctor wants the different pictures, you can see the two phenomena, all the three phenomena, that there are different parts of the galaxy that light up under different wavelengths. Some parts are more prominent. Some things like the center of the galaxy is not visible in radio for some reason. It's very strong here and here. And the fact that you're getting complementary information. And if you look carefully, you will find that there are certain things in certain parts of the galaxy which are not visible in any wavelength except one particular wavelength, right? And I'll show you a couple more examples. So this is another galaxy. This is a galaxy we are seeing face on. It's called the Whirlpool galaxy. And again, you can see that when it is studied at different wavelengths across the electromagnetic spectrum, different parts or different phenomena. So in some, the optical light is coming from the stars. The ultraviolet comes only from the hottest stars, and the X-rays come from the gas in the galaxy. Hardly any X-rays comes from the stars. So you won't see any of the stars here. You will see mostly the diffuse gas in the galaxy. And radio comes from cold gas, hydrogen. And so it traces a different aspect of the galaxy. So this is what the astronomer learns, how to interpret the data from different wavelengths and combine it into a composite of the object, just like your doctor would want to do. So here is one more example. This is now a nebula. So this is it's again a very famous nebula called the Crab Nebula, which is in the constellation of Cancer. It's an object in our own galaxy, and again, views in different wavelengths show very different pictures. And in fact, it hosts what is called a very special kind of star called a neutron star or a pulsar. Maybe I'll get to it a bit later on. And that is an object that you can see predominantly only in radio waves, for example. So, so we can ask, well, this is nice, but when it all started, we had, you need these two things, the detector. You need the equivalent of the eyes to see the other wavelengths. Okay, and that was one big problem, that we had only the natural detectors are only for optical. Our eyes are not sensitive to any of the other wavelengths, and so we had to wait till technology grew to the level where you could make detectors for different wavelengths. Of course, first you have to understand that there was a spectrum beyond light, and then you ask, well, how do I detect these other wavelengths? Okay, and even in optical, we evolved from our retina being the detector to the detectors being on photographic plates. So at the focus of the telescope is not the eye of the observer, but there's a photographic plate which captures the image. Or even later, CCD cameras now. Many of the CCD cameras that we now see in our phones and all that, a lot of the technology development for CCD cameras was driven by the need of the optical astronomer to have very high quality CCD at the focus of the telescope, so that you can get a nice picture. So that is optical. So you ask, well, how did we learn how to detect other wavelengths? Okay, and some of that happened due to pioneering efforts of different scientists, and I'll come to that in a moment. And but there is the other problem, which is you have to ask, do all of these wavelengths reach us? Okay, they may exist, and the simplest thing that we all know about is the ozone layer or the ozone hole, right? We know that that layer is the one that blocks the ultraviolet from the sun, prevents it from reaching us and causing damage to us, to our skin. And so when there is a hole in the ozone layer, we get worried, because now the ultraviolet can come through, right? Sun emits ultraviolet to a reasonable strength. Okay, so so there actually, just like the ozone layer blocks ultraviolet, there are other parts of the Earth's environment, either the Earth's atmosphere or the ionosphere around the Earth, which happens to block different wavelengths from coming in. So this is a diagram which shows what is called opacity. So when the opacity is 100%, that means that wavelength is going to be blocked completely from traveling through. And so this is again the electromagnetic spectrum, the wavelengths going from the shortest to the longest, which is radio waves on this side. And what it shows is that there are only some parts of the electromagnetic spectrum where there are windows where the radiation, the opacity is low enough that the radiation can reach the ground if it is coming from celestial objects. Okay, so one is of course the optical one, the very narrow window here that we know, but many other parts of the electromagnetic spectrum are completely shielded, blocked by the Earth's environment, and the only other big radio from the Earth, and this is like a trace that as he moved his shield around, you could see the peaks of the radio signal, and from there he made the inference that what I'm seeing is something out there in the sky, and not something on the Earth that is producing this extra noise that is disturbing our equipment. And that is the first time people realize that we are actually receiving radio waves from a celestial object. And that started the whole field in the late 1930s. And in the beginning, again, this is the thing that without the technologies, this could not be done. So in the beginning, this field was driven completely by engineers. For some time, the traditional optical astronomers never gave it much importance. Okay, fine, you found some radio waves. But we've got these big optical telescopes that take all the information that we want to know about the universe. But slowly, people started doing this, and this is another engineer in the lab. In his spare time, as a hobby, he built this in his backyard.
So this looks a bit more like what we think when we think of a radio dish antenna. And with this, he scanned the entire sky and made the first map of where the radio waves are coming from in different directions in the sky. And so this started the whole field, which has then of course grown. And like I said, pretty soon it became clear that we are getting a complementary view of the universe using radio waves and what we get with optical. And so that point that I was making, that you could see some objects which are common, but many objects which you would never knew existed came alive and became visible because of the radio signals. So what I do now is jump a little bit and just talk about how we use the tools. So when you look at a typical radio telescope, in principle it is no different from your satellite dish receiver. Right? We all have it sitting on our rooftops. There is a dish with a certain shape, it's parabolic, and the parabola is there because it brings the incoming radio waves to a common focus point. This we would have again studied in maths, that a parabola has a single point focus, and so the waves get focused here, and then they are picked up by a small receiving element, an antenna. So typically it's a dipole, or sometimes it's a waveguide horn antenna, which converts the electromagnetic wave into an electric voltage. Okay? So that is now so that is what your any receiver does, whether it's your radio receiver, so our mobile phones have a small antenna inside it. In fact, there is more than one antenna, one for GPS, one for FM, one for your actual main mobile signal, and so on. And every device has that. And so it converts it into electric voltage, and then you amplify that voltage, and in our case, man-made transmissions, you extract the information out of it, whether it is your audio that is coded on it, or the video signal that is coded on it, and so on. But at this point, the differences between this and what we do start showing up. And the main driving force behind the difference is that unlike our man-made transmissions, which are fairly strong signals, because they are designed such that with a small antenna you can pick up enough signal, that you have enough sensitivity that you can detect information that you are looking for. These signals, because they are coming from very, very far away, remember I talked about thousands of light years and millions of light years away, and the bulb being taken further and further back becomes fainter and fainter. These are very, very weak signals. There are various ways of looking at it. If you are into actual physics, this is the measure in watts per square meter, like the power density that is falling per unit frequency. But forget all that. If you ran a reasonably large radio telescope collecting signal from a typical radio source running for 1,000 years, it will collect 1 millijoule of energy. Now 1 millijoule, probably you can understand, it's several times smaller than the amount of energy you will use to heat up your morning cup of tea. Okay, so each morning when you heat the water to make your tea, you are using thousands of times more energy than what this radio telescope is collecting over 1,000 years observing these waves sources. So this is the thing to keep in mind, that we are looking at very, very weak signals, and because of that, there are changes to this very simple picture of this, 2-foot big parabolic dish with a simple receiver. So now we go back, and so if you have very faint signal, you want enough of it, you build a bigger and bigger aperture. So you can collect enough of that signal so that it becomes easy to measure. Right? So we end up building antennas which are tens to hundreds of meters in diameter as compared to your less than a meter size satellite dish. That is also not sufficient because there is another enemy hiding here, which you know also, that when you are, and the same problem that Carl Jansky was trying to overcome, and you see that in your radio set, there will be sometimes noise. So noise comes from various things. In that case, it was coming from outside. But any electronics that you put here to amplify the signal and detect it, any piece of electronics has intrinsic noise. And that noise, we don't worry too much in our communication systems because our signals are strong enough compared to that noise. But here, since we're talking about very, very weak signals, the noise dominates over those signals. And so it is like saying that, well, I'm trying to speak to you, and there is a very strong hum in this room, then you will not hear me. Okay? So if that background hum is too loud, then what I'm saying, that signal is lost. And you have to reduce that hum, or you have to amplify my voice to the level that it goes above that hum. But if you're just going to pick up my signal and amplify it, and the hum is all around, you will amplify the hum also. Okay, so you have to now do this in a careful manner. So you say, well, let me put you in a room where the hum is intrinsically as low as possible, so that you are not fighting against a situation where the noise is dominating over the signal. So we try to build low noise electronics. Okay, you say, what is low noise electronics? And that is the technology in itself, that how you build low noise electronics. In the end, if nothing works, you have to cool it to very low temperatures, because a lot of the noise comes from random motions of the charge carriers, electrons in the p-n junction, or random motions. And the only way to reduce those random motions is to cool the system to very low temperatures, so that random motions, the energies of the charge carriers come down. Okay. So these two real problems. We have some plus points. So unlike man-made transmissions where you transmit with some narrow bandwidth because the signal is of some finite information content, many of our signals that we are receiving, so like we saw, the sun is emitting over the entire optical window. So you will see, although sunlight looks yellow, it is going all the way, including into infrared and ultraviolet. So if you can collect that energy over the entire range of wavelengths or frequencies, you will get more signal. And so many of these phenomena are what we call broadband. So you can increase the amount of frequency coverage over which the telescope works, and you can boost the amount of signal. The other thing that works in our favor, unlike our man-made transmissions, is that information content is not changing with time. So when I'm speaking, my every new word is a different piece of information. But if you look at the sun now, you look at it 5 minutes later, you look at it next year, it will look statistically the same. There is no change in the information content. So if you gather that signal over the longer duration of time and keep adding it, then you can boost the signal as compared to the noise. Okay, so if I was, just making a single monotone sound, then you would keep adding it, integrating it, and you would make it rise above the background hum. Okay, so these two techniques we use to increase our sensitivity. So remember, all this is that quest for sensitivity, so that fainter and fainter signals can be detected. Okay. So this leads to these very large telescopes with very complicated receivers, working with large bandwidths, observing for long durations. And those durations can be hours, days together, that you're following the same source in the sky to build up enough signal so that you can detect it easily. Now, there is the other thing that we want now to come back to. So you remember there were these two reasons to build these bigger telescopes. That other one was the resolution. So you want to be able to see the finer details of the objects which are too close by to separate. And there, if you remember that formula had a wavelength in the numerator. Okay, so if the wavelength becomes larger, then for the same diameter, your resolution becomes poorer. And now we have jumped in wavelength by several orders of magnitude. From optical window, which is of the order of nanometers, we have gone to radio window, where the wavelengths are of the order of meters. So this then produces a big problem, that even if you use a 100-meter size antenna, so I showed you optical telescopes, you're going to tens of meters. So we are talking now about 100-meter size antenna. But if it is operating at radio wavelengths, the resolution is very poor. It is about half a degree. Now you ask, what is half a degree resolution? So we go back. So when you look at the moon with your eye, you will see a picture like this. If you see it with optical, you see this. With a radio telescope looking at the moon, you will see worse than this. So half a degree is the size of the moon, actually, angular size of the moon. So that means that with such a big telescope, you will not be able to make out any details on the moon. It just looks like one fuzzy sphere or circle, and you will never get a picture like this. So now you see, so the optical guys are going to tell you, good, you have, but you can't see as nicely as we can. Okay, and then, if you go to the doctor and you say, look, I got a poor quality MRI, it's very fuzzy, it's no use to me. I can't compare this against the ultrasound image, for example. Okay, I want both images with similar resolution, then only can I make use of it. Okay, so this was a challenge. And so you say, all right, how big can you make this film? Okay, 300 meters, 500 meters. It becomes difficult because this thing needs to move and look at different directions in the sky, to look at different objects and follow them as the Earth rotates. So this challenge took a while to find a solution. And finally, it was found by somebody who got a Nobel Prize for that idea, which is to say, all right, I can build a 30-kilometer size radio telescope. Let me do the following. Let me build several smaller radio telescopes and place them over a 30-kilometer region, and then combine the signal from them in a manner whereby I can then synthesize an image which would have the same resolution as the 30-kilometer size telescope would have. Okay, so you say, all right, okay, so that was a brilliant idea. So what happens there is, instead of being limited by the individual telescope's size, you are now limited by how far you can spread it. So that in that denominator, the aperture of the telescope gets replaced by the area over which you are placing them. So now you can go and say, well, I can place them over tens of kilometers separation, then I can get the resolution of a radio telescope whose size is tens of kilometers by building only telescopes which are few meters in size, but many of them. Now you can ask how many and how come you can get it without filling this entire area with telescopes. So those are the tricks and the technology and the concepts and the mathematics, but it is such that that idea, it actually has its basis in Fourier transform theory, if you're familiar with Fourier transforms and so on. And it is a concept which is also very parallel in computer tomography, medical imaging, uses the same concept. So it came from the theory of Fourier transforms. It was first used for this idea by Martin Reich, who got the Nobel Prize. And then it was realized that in other areas of imaging, because here also we are going to do imaging with enough resolution or clarity. So other areas where similar medical imaging challenges are there, and of course most widely used in medical imaging, but in many other medical imaging applications. Okay, so now what we do is we just encapsulate all this that we have learned by looking at a case study, which is our own GMRT radio observatory. And so the GMRT observatory, not too far, and you're welcome to come over any time. It's 2 hours drive from here on the way to Nasik. And if you've gone past and you have looked around, you would have seen some large antennas near the highway. You can see quite a few of them from the highway itself. And they look like this. And so that's our giant meter wave radio telescope. It operates in some part of the wide radio window that I showed you, which is visible with ground-based telescopes. It operates over this low frequency part of it. And in this range of frequency, it's one of the largest facilities in the world in terms of its sensitivity. So it has 30 antennas, each of 45 meters in diameter. 45 meters itself is not small. Okay, and they're fully steerable dishes. And it is spread out over a 30-kilometer region. So again, that same idea that I can spread antennas out over a big enough region, then I can get a higher resolution. We talked today about Atmanirbhar Bharat and Make in India. This is 30 years ago, fully made in, designed, developed, and built in. It is open since 2002 as an international facility. It is used by astronomers from all over the world who are with whatever ideas they have about what they can study about the universe. And we've been constantly improving it, and in 2018-19 we completed a major upgrade which, that's part of modernizing and growing with technology and keeping the facility active. So today, of course, you have to Google anything and everything, if not ChatGPT. But if you do this, Google will show you some nice images. But like I said, nothing like an actual visit. So this is that central part of the array where you can start seeing some of the antennas. And you can zoom this. These are the closest antennas. And so this is the main central building. So the signals from all, like I was saying, you have to process the signals from all the antennas in order to make that image with the resolution. So signals come on optical fiber from all the 30 antennas. They are finally, converted, amplified, digitized, and there's a whole lot of digital signal processing that goes before you can make those images and see the results. And all of that is done here, and then there's a copy of the data kept there, a copy of the data that comes to our center here on the university campus, and from there it is disseminated to users all over the world. And so this is a view of the central antennas. This is a close-up. So now you can see what 45-meter diameter means. And most of the, like I showed you in your satellite dish, the initial place where you pick up the signal and convert it into voltage is right there at the focus of the parabolic dish. And this is at 30 meters height above the ground. You need a special crane to reach there and work on the electronics over there. And by now you may have got a sense that if you have to build something like this and make it work, it is a combination of all kinds of technologies. From mechanical engineering to make such. So this weighs 100 tons and it's fully movable, steerable 100 tons. And then you have to precision control it. Where is it pointing? Is it pointing at the object that I want to study? Can you follow it accurately as the earth rotates? So all of that requires precision servo systems that will do this. And then all the radio frequency engineering to pick up that train signal, amplify it, optical fiber transmission technology to transmit those wideband signals, digitize them, and then high-speed digital electronics to process it. So for example, the total digital electronics that we have there is handling data at 20 gigabits per second sustained. So those of you who work in these kind of things, that is sustained 20 gigabits per second, and about 20 teraflops of computing required to do the analysis of that data coming from the antennas. And then finally, you have to control this whole thing. If this becomes as complicated as a complex factory where different things are happening, you have to control all of it, coordinate the activities, configuration. So there is a very sophisticated control system for controlling it, both hardware and the software. And then finally, when you get the data, there is very sophisticated signal processing, image processing algorithms, and computing required to finally make these images. And just to keep in mind that GMRT, although we keep sort of modernizing it, is already something which is like 20 years old. So today, what we are working on, which I won't have time to go into, the next generation radio telescopes, are much more challenging in many of these aspects of technology. Okay, so this is just a bit of historical perspective, inaugurated by Sri Ratan Tata, who is the chairman of the Council of KIFR, which is what we are part of, and running for many years, used by people from all over the world, from more than 30 countries that astronomers have used. And you can ask, how is a facility like this used? So it is purely based on scientific merit. So anybody, anywhere in the world, they think of an idea that, look, with this kind of facility, I can probe this aspect of the universe by doing this kind of an experiment, and I would like to request time to carry out this experiment, and then they will analyze the data, make their findings public in a publication. So that's how this kind of science research works. And so we run this cycle twice, 6 months cycle, where proposals are invited from anybody and everybody in the world, and then there's a committee that evaluates the proposals. It asks for international experts to review them, give the comments. The proposals are ranked by their significance, and then time is allotted on the observatory, and then we make a schedule for how observatory should run for 6 months, whose experiment will be scheduled when, and then the whole thing runs just like you would automate how a factory runs, and then run the things. Okay, so now you can see that the complexities and the things involved here have a lot of synergy with how you would run many other things in the world. And typically, so now when you open something there's a demand versus availability issue. So you say, I have 6 months of time, please give proposals, and we get proposals which ask for prototype required is 2 times of 6 months. Now what do you do? So there is competition, and that is the job of the committee that decides. So this typical oversubscription is this supply to demand ratio is typically more than 2. And so the best of the ideas, the best proposals then get finally accepted and scheduled. And I come back later to show you, you may say at this point, tell us what you're learning from all this. I come back at the end with just a summary of high level of what you learned for the universe from various things. But just to point out a couple of interesting things. So we not only study natural phenomena, there once in a while where we are called on to do service for space missions. And you would have heard this, oh, Voyager signal got lost, then it was recovered. Okay, what happened? So many times when space probes go out, again, those signals become weaker and weaker. So if you are going to the moon, okay, the Chandrayaan mission is not so bad, but when it goes to Mangalyaan, the signals are much fainter, and you need to be able to receive those signals and process them and command the spacecraft. So often the most sensitive radio telescopes do get called in for doing service. So mostly space research organizations have their own facilities. So ISRO has its own large antenna near Bangalore, which is called Earth Station, which is what they use for communicating for satellites. But this is an example where we worked with NASA for a European space mission, which went to Mars. So this is very similar to our Chandrayaan 2 and Chandrayaan 3, where there was a orbiter going around Mars and then a lander module to make that landing. And that lander module is emitting a radio signal, it's a beacon. And so you can pick it up and track its health, whether it's alive. Just like what you saw on your screens for the Mangalyaan mission, you would see a signal. It's basically a radio beacon that's coming back, giving you information about where the probe is, and you can infer what the speed is, you could see the speed and all of that. The point to realize is this is 3 watts. 3 watts is typically what your mobile phone is. So if you take your mobile phone and go to Mars, if you're going to do that, we'll be able to pick up that signal. So this is just to drive home the point that the sensitivity of this is at that level. Okay. And this was able to track this landing, follow the velocity. Unfortunately, like Chandrayaan 2, this also created a disaster. Just 50 seconds before touchdown, the signal was lost and the spacecraft went out of control, just like what happened to our second Chandrayaan mission. And then there is the other point, which I think you all may have been asking. What do you guys do? Why are you looking at only natural phenomena? There must be people like us out there. And there's always been a big curiosity that can we detect such intelligence? And people ask what's the best way of doing it, and we go by our own sort of way we live. We use radio for communicating, as you have seen. And so we think that if there is an intelligent being out there, it's trying to communicate, they must be sending radio beacons, and so can we pick them up. Okay, so a fair bit of radio astronomy time and facilities are dedicated to this search for extraterrestrial intelligence. It's a very challenging and complicated task because it is much worse than a needle in a haystack kind of a problem. When you're searching for a needle in a haystack, you at least know what the needle looks like. You know that if I see something which is like this, I know I found a needle. Okay, I just have to search hard enough. Then you don't know what the needle is. You don't know what that signal will be. You You can only guess at the way we transmit. So what we look for is, so when we transmit, so my voice, when you decode it, will be abrupt changes in the frequency or the amplitude when I am speaking, as compared to this background noise or hum, which will be continuous kind of a signal. So we build algorithms which try to detect sudden and natural changes in the signal. You say, what are you looking at when you are looking for this? So again, we don't know where to look also, which is part of the needle in the haystack issue. So, and I'll come to a bit later, that there is now some feeling, okay, look at that star, likely to harbor life. It may likely to have a planet which is like the Earth going around it. But these are all presumptions that you need a planet like the Earth act on a star which is like the sun in order for life to flourish. It is not known, and there are models and theories which say that life can be there in other different forms as compared to this carbon, nitrogen, oxygen cycle with the kind of environment that we need for life. But this is always in the back of the mind of the astronomers. Okay, so just very briefly go and because you will be asking how do you show all those images of gamma ray and X-rays and so on, which are not accessible from the Earth. And as you can see, and you would have guessed, and you probably know, that the only way to do this is to send the telescope into space, well above this blocking atmosphere of the Earth, which is blocking the radiation from coming. So that is how this happens. And this again, of course, you need to say, how do I detect gamma rays? What is a detector? How do I detect X-rays and so on. So all that was learned with time, with technology. And then the technology now allows us to do all this kind of stuff. So you have ground-based telescopes. You have telescopes which live for some time and they are flown on high-altitude aircraft. And then there are telescopes which live for longer when they are flown on satellites, and, including balloons. And this is now the way we get all those images that I showed you of the galaxies in the nebulae at the different wavelengths of the electromagnetic spectrum. And these are examples. I think you are all familiar with the Hubble telescope. We've heard so much about it. It's been there for decades now. But there are similar telescopes which work at all different kinds of wavelengths. So whether it is gamma rays, X-rays, optical, microwaves, and so on. And this is of course a field which grows with growing technology. And one example of this is this comparison. So Hubble telescope, you all may have encountered some of the other, but recently you would have heard about this James Webb Space Telescope. And just to show you how this interplay is with technology and what man can do. This was in the 1990s, right? And this was launched just 4 years ago. Okay, and if you look at their, I have come back to the slide, but this fellow it's a marvel in technology just by itself. Okay, it is sitting at a distance which is this one doesn't have that at that Lagrange point, which is several million kilometers. The Hubble telescope is just going around at some 400, 500 kilometers above the Earth, circling the Earth. This guy is at a Lagrange point. It's circling the Sun at a constant place where the force of gravity between the Sun and the Earth and the other planets is balanced. So it can, those are called Lagrange points in the solar system. It has been sent there via, of course, the space probe. But what is interesting is that it has got a mirror which is quite big. Okay? And this all went, I don't know if you saw the picture of the videos, it all went packed and it was opened and unfurled and this was made operational. It has amazing challenges. So this, like I was saying, the electronics here needs to be cooled. Okay. Now there is the sun out there. So the moment you see the sun, it will get heated up because it's not sitting very far away from where the Earth is as far as the distance the sun is concerned. So it has got a sun shield. this sun shield, so on the hot side is 85 degrees centigrade, on the cold side is minus 233 degrees centigrade. And there is technology to manage that. Okay, and and this is all, you can even ask, how do you even test this kind of stuff that you build on the earth, that it will work over there under these extreme conditions. So this is what is possible today in terms of the technology. So 6.5 meters size telescope. Hubble telescope is just about 1 meter. Okay, and the result it is producing is amazing. I mean, every so often you see a news item where the JWST has found something new and interesting and exciting. So these kind of things are possible. You may also ask, okay, does India have a presence in space missions? And we do. It's a relatively modest presence, but it is there. In 2015, India launched the AstroSat satellite, which was basically a payload which had X-ray and ultraviolet telescopes, which again cannot work from surface of the Earth. And this has been doing good science. We've been working for 10 years now, although its mission life was 5 years. Just like Hubble's mission life was, nobody expected Hubble telescope would live for 30 years. So of course, there have been refurbishing missions to the Hubble. You can't go to JWST and so when you design this, it's a few $1 billion worth of stuff going out there. It has to be designed that there is no repair possible. Either it works, if it fails, you must have self-repair mechanisms, otherwise it's gone. There's nothing you can do about it. In Hubble, they were able to rescue it because you could send humans to go there and repair it. So, this is and this was launched just last year, Aditya L1. This is a mission dedicated to study in detail the properties of our own sun. And this is again positioned in one of those Lagrange points L1. And it is parked there now, and it has started producing the first of the science results. Okay, so at this point, I think your curiosity will be piqued enough to say, hey, what all have you learned from doing all this stuff over these years? So I'll just give you a very high-level sort of tour of the universe, just pointing out some of the interesting things. There's no time to go into various details of what we learn. So this breaks into things like what are the constituents of the universe, what is the size and scale of the universe, what is the age of the universe, and how has it evolved over time, and is there stuff that we still don't know about the universe? Okay, so those are the things I try to cover in a relatively brief manner, but we can discuss more. So contents. So we know that we have a solar system which it has a star and planets, and we know there are many stars that we can see, and there's always the question, do all these stars have planets? Is that the rule, or are we an exception? And if so, what kind of planets? And this is a field that has grown tremendously in the last 15-20 years, and we now know star systems which you can compare with the solar system. Okay, this guy has these kind of planets, so many of them, and then there is this definition of what is called the so-called Goldilocks habitable zone, that it should be at roughly this much distance from the stars, so it is neither too hot nor too cold. It should have a composition which is not a gaseous giant like Jupiter, but is more a rocky planet like the Earth. And then, can I probe its atmosphere? What does it have? Does it have methane? Does it have oxygen? So this is the level at which we are now reaching to be able to start to answer these questions. And so there is now a list of potential habitable worlds. Mind you, this is all within a few light years around us. We can't do this at any further distance in our galaxy. So we're just probing a very, very small fraction of our own galaxy and asking this question, can I find what we think may be habitable planets? And then you ask, what further can I do to probe them and see if I can find some telltale sign of life. And like I said, one of them is to look for radio waves, but now these techniques have become sophisticated enough that can I probe the atmosphere, what kind of gases does it have, and so on. And then can I ask that, oh, this looks like a combination which would have a life. Okay, beyond that you ask stars. How many stars in a galaxy? I don't know if anybody has taken a guess, but there is 100 billion stars in our galaxy, just in that, in the Milky Way galaxy. Okay, that's a staggering enough number. You say, well, what kind of stars? And they come in a huge variety. I mean, we are used to our sun, but stars which are 10 kilometers in size to 100 times bigger than our sun. Our sun is, thousands of times bigger than the Earth. And you say, how can you have a star which is the size of Pune city? There are such objects. Okay. Then you say, how can they exist? And so this is the beauty. So the first of these, which are called neutron stars, pulsars, they shine in radio. They were detected first time when radio astronomy started. Nobody had heard about them or imagined. Then of course theories came. So Chandrasekhar, our Nobel Prize astrophysicist in the University of Chicago, he was one of the first persons to postulate the theory that how big enough normal stars could end their life and become neutron stars. So there's a star which is made up entirely of neutrons. I think we all know enough basic thing that we are made up of molecules. Molecules are made up of atoms. Atoms are made up of electrons and protons and neutrons. Protons and neutrons live in the center of the atoms. The nucleus, that is the place which has the highest density. The rest of the atom is mostly empty space with electrons, very lightweight electrons going around. So if you crush matter, where you can collapse, break the molecules, break the atoms, and all that is left is a sea of nuclei. So you say, what kind of force is required to crush matter so that molecules vanish, atoms vanish, and only nuclei are left? So such things happen. There is physics which makes all this happen, and you get objects like this. So the entire, so this object has as much mass as our sun, okay, which is millions of times more than the Earth. It is packed into a 10 kilometer size. 10 to the 14 grams per cc. So 1 teaspoon would be some 100 tons. Okay, so you can say, this is science fiction. But the point is, using those fake signals that we are picking up, we are able to use physics, maths, logic, and inference to come to all these conclusions and show that it has to be this kind of an object, it cannot be anything else. That can only explain the properties that we observe. So they are very exotic kind of stars. The sun is thought of as a very garden variety star in the comparison with all kinds of the big giant stars that exist, 100 times bigger than the sun. They have amazing sort of life history. So this is the other thing. What kind of life do stars live? How are they born? How do they evolve? How do they die? Even the sun will sort of quote unquote die after 4.5 billion years. So we don't have to worry about it. But but all this is theories that have been worked out and understood, backed up with the data. Okay, we go beyond that. We say, are there anything else besides stars? And there is gas in a galaxy, because gas is the one that from which stars form, hydrogen gas. So we think of us and we say, okay, this element, that element, this compound, and all that. The universe is 99.99% hydrogen. Okay, so you say, wait, how can it be? When I look around, there is very little native hydrogen around me, the Earth. The sun is predominantly hydrogen and helium. And so these are gas clouds, predominantly hydrogen, but with some elements added in it. And you can ask, where did those other elements come from? So you can ask, where did the carbon, nitrogen, the silver, and the gold that we see come from? They all come from stellar processes. So the joke amongst astronomers is, if you give a gift to your wife a golden necklace, that gold was created in some star, in some stellar explosion somewhere in the universe. It's not formed by any other process. So this is the kind of thing that one learns. And so these are very interesting looking shapes, but these are all physical objects out there in the galaxy, in our galaxy. And then and there is as much mass in the galaxy as the total of those 100 billion stars. So about 50% of the mass of the galaxy, in our galaxy at least, is still gas, and 50% is stars, and that is that 50% is that 100 billion stellar masses. So then you say, okay, fine, all right, can we go beyond that? How many galaxies in the universe? Okay, so again, we will talk in billions. So today we believe that there are 200 billion galaxies in the universe. So how do you make an inference? Again, that is what the job of the astronomer is, based on the limited data that we collect. How can you infer? Okay, then you say, how are these organized? So that brings me to another point, that what we found is that there is a hierarchy of structures in the universe. So we start with the planet like the Earth. The planet is part of a solar system, a stellar system, that is the sun with its planets. Sun itself is a part of what is called a stellar group of stars, which are bound. So the Earth is bound to the sun by gravitational forces. These are stars which are bound to each other by gravitational forces. That means they are interacting with each other. It's a star cluster. And then there are many such star clusters which make a galaxy. So the galaxy is an assemblage of such groups of stars. And then, as we say, that these galaxies themselves are organized in groups. So these are called now galaxy clusters. So they will be. So our Milky Way is part of a small local group which has Andromeda galaxy and two other galaxies. So again, they are close by enough that they interact by gravitational force, but they behave like a group. Then there are other such groups of galaxies, and so the universe has a structure. Then the clusters are clustered in superclusters. So it is like saying, you know, that I have a house, then I have a locality, it is part of a city, city is part of a conglomerate of towns and cities, and so on and so forth. Okay, so there is a hierarchy of structures up to what is called superclusters of galaxies, and then we don't know. So then we say all of these are part of the universe, and then you say, okay, is there another universe? Okay, so those are some of the open questions. So there is what we call the observable universe. That is what we can observe today and what we can infer. There may be stuff beyond that, and that is what the last part is. But before I go there, there is this thing that how does it all tie up? Okay, was there a beginning and is there an end? Okay, and we think we know enough to say that there was a beginning, and then again you will have heard this something called the Big Bang, and you say, how did you all imagine all this, that there was something called a Big Bang which created the entire universe that we see today? How did it grow and expand? What was it in the beginning? Okay, it was just a soup of very energetic particles. From there, how did galaxies, stars form? How did they evolve to what they are today? So all of this has been learned by this technique. And again, as I told you, that when you look to fainter and fainter objects, you're seeing further and further back in the universe, so you can actually see some of these guys. Because that signal has now only reached us. It started some billion years ago. And rest of it is based on inference. That in order to see this should have happened before that. So then there is a number, again billion. So 13.6 is the current number about the age of the universe. That is, when this event happened versus today. So, and then again the attempt is to understand what all happened during those 13.6 billion years as accurately as possible. So at this point, this gives us a sense of our place in the universe. It also, you may say, all right, good, you figured out everything. Unfortunately, that is not the case. When we ask that, do we understand everything that we see? And the answer is no. In the sense that we see evidence in the data that we collect, which is not explainable by our current understanding of matter and radiation. So there are concepts like dark matter, which some of you may have heard about, that the universe has a certain amount which is in dark matter, and then there's a concept more this thing called dark energy. Can you say what does this mean? And frankly, even some of us don't fully understand that. But what we do know is that in order to explain the total observable phenomena, which is confined to this. So all that I talked about, whether it is hydrogen or anything else, is just 4.6% in terms of the mass energy constitution of the universe as we understand it today. And so you say, is there a future for astronomers? Yes, there is plenty more to be learned and understood. And so that quest continues. And I think that's true in almost any area of science. I mean, you can dive deep into the human body and into the cell and into the inner parts of the cell, and you'll see the same, a billion scale factors coming in trying to understand what happens down at the micro level, and then this is at the macro level. And in all of these areas, there is things yet to be learned and understood, and that is why it, whatever you say, keeps us awake at night, or it keeps us going, saying, look, let's build something bigger and more powerful, so that we can see beyond what we can and infer about some of these things which we just call them dark because we don't know what they are and how to explain them. Okay, so I'll stop here, and then we can discuss further if there's something that you would like to know more about. And I'll just sit down for a few minutes. Yes?
How do you come to the estimate of 4.6%?
Yeah,
You don't know anything about that.
Yes, so it is like just doing a total balance. So you say that in order to explain the phenomena that I'm seeing, there must be this much percentage of this additional factor present compared to the percentage of the known matter. So I'll give you one simple example. So you say, how do you at all infer that there is something called dark matter? Okay, because by dark it means it does not interact with like electromagnetic or light. It does not emit any light, any X-rays, gamma rays. It does not absorb anything. So how do you detect it? So what works is that it still interacts gravitationally. So it is then has some gravitational mass properties. So therefore, if normal matter and dark matter are present, they will interact with each other. So so in a galaxy, there will be the normal matter like I showed you. There will be dark matter also. And what has been found is that when you look at a galaxy and you say, I've seen all the matter, whether I'm probing it in optical or in radio or whatever, and I see that there is this much matter, this much density of matter in this galaxy. But the way the galaxy is rotating, the speed at which things are moving in the galaxy, tells me that there is more mass here, going out to well beyond the limit to which I can see light or radio, and even at the center somewhere. So then the inference is that there is something which does not emit radiation, which is present there, and its presence is inferred. There you can then infer, is this mass more than the total visible mass that I can see? Is it less? So then you can start getting these ratios. So it is a complicated chain of inferences based on some basic observations. I mean, so unlike a lab where you can go and change conditions and do things, this is lab given to us, and you just have to observe and make inferences.
So is this kind of balanced by mathematics in the sense that, unless I add this constant, the equation doesn't balance?
Yes, effectively in theories, so there will be a constant in some Einstein's equations or some equation that says unless you put this fellow there, you cannot explain the phenomena that we see. And this is therefore lambda dark matter. So there are terms like that for those terms in the equations.
There was one thing about GMRT. Is there any notable or an achievement, which you can just say that GMRT has done in last 30 years and something which is?
I can. I mean, I didn't Google because the result, whatever knowledge I talked about was just at a very high level. But there are some interesting, notable things that the GMRT has done. So, for example, I talked about these neutron stars. Okay, so they are detected in radio only. So we found a good number of such pulsars in our galaxy. In fact, one of the earliest ones we discovered shortly after the GMRT was commissioned, 2003, 2004, two of them, and I was part of those experiments as part of the team. And some of them had very unique properties, which made them very special. And again, what happens is, you can ask, all right, you found a neutron star. At some point you say, okay, big deal. Okay, you found another one, okay, big deal. Then you say, okay, this one is special. Okay, why is it special? Because it is in some special environment, or it has some special property, which helps you to understand some other aspects of physics. So one of the things that happens in these things, we think of our solar system, one star and planets, but that is not necessary. There are systems where two stars are within a one solar system, multiple stars also, 3 star systems are also known. Then you say, okay, fine, all right, so what? Now, these are two fairly heavy objects which are orbiting around the center of gravity. And Einstein's theory predicts interesting phenomena that happen when very massive objects are close to each other. So you can ask, people say, well, Einstein's theory was an improvement on Newton's theory. So what was wrong with Newtonian physics? The Newtonian physics works very well for almost all the things that we know of. It breaks down where gravitational potential becomes very strong. And that means if you have two very big gravitationally bound bodies coming reasonably close to each other, that's when these potentials start exceeding. So if you went very close to the sun, you would experience a gravitational potential where these relativistic effects would become important. But you don't have such a test case. Even if Mercury were to fall any closer, it would just, but in the orbit of Mercury, that was the first time, if you know, that the evidence for Einstein's theory was shown in the solar system. It's a very, very tiny effect. If you want to see that effect more clearly and you want to ask, is Einstein's theory the final word? Then you need to go find systems where instead of Mercury, you have another star there. Okay, fine. So you say, fine, I found a system with 2 stars, but how close can they come? Okay, the stars are still very big. Can I find a system where these 10-kilometer size stars are there? They're coming within maybe 1 million kilometers of each other. So then these objects become very special, because now so you say, can I find one of these around a black hole? Then these distances can shrink even further at some point, and that's what happens if you have seen the first result that came from the gravitational wave. I didn't talk about gravitational waves and other ways of probing the universe because I was confining myself to the electromagnetic window, but today there are other ways of learning about the universe beyond the electromagnetic window, which is gravitational waves, which are not electromagnetic waves, and energetic particles which bring information. But these are now objects, so you can have a situation where these two heavy masses come closer and closer and closer, and they're losing energy, and they're in spiraling, and at some point they will coalesce. So they will literally merge. And if you can get the signals up to that point when they are merging, then you can actually study many of these strong field effects. And so that has been one of the holy grails, that who can show that Einstein's theory is right up to next decimal point, or is it going to get violated at some point? Do I need a better theory? And so you say, how can you answer these questions just sitting on the earth and just observing? So you can actually do this. You can actually say that, so these are laboratories out there which allow you to do this kind of a probing, which you could not imagine otherwise. To the level of asking, the level at which you are asking these questions now, is this theory valid in 1 part in 1,000, 1 part in 10,000, 1 part in 1 million? Is there deviation? Do you see any deviation from what it predicts? Okay, so this is the thing that drives many of these kind of discoveries. But just to come back, so we found a few of these interesting pulsars. Then there are other areas where geometry has made very interesting contribution, finding some interesting kind of magnetic stars. Then a lot of investigation of galaxy clusters, because in the galaxy clusters, the gas inside the cluster gets heated, emits radio waves, and you can study these very clearly. There is a certain class of galaxies called radio galaxies. Like I said, I didn't have time to go into all that. So a lot of work has been done to do that. Just to come back, so the gravitational wave detectors, and you would have heard about it, that there's one that is coming up in Hingoli, LIGO India, which is the third detector out of the two detectors built in the US, which were involved in the original gravitational wave detection. It's under construction now. That is one way of probing gravitational waves. There is another way of probing gravitational waves. So I didn't say this again. These pulsars, the way we detect them is that they emit pulses. So you say now there's another new thing. And the reason they emit pulses, they are like lighthouses. So if you see a lighthouse has a fixed beam from a source of light going out in a given direction. And as the lighthouse rotates, you see pulses. In this case, these are stars where at their magnetic pole there is a phenomenon which occurs which produces radio beams, just like a lighthouse. And of course the star is going around and it is emitting pulses. Now again, if you want, it's a 10 kilometer size star, it is rotating, Earth rotates, the sun rotates, okay, we go around once a day and so on. These guys go around once in a second. The fastest one goes around 700 times in a second. That's faster than your fastest RPM motors. This was the science fiction, 10 kilometer size object with as much mass as the sun. How can it be spinning, at 1 hertz or 100 hertz? They're there. And you can infer all this by picking up these pulses, measuring the period of the pulse and the timing of the pulse, and inferring this. Now, what makes it more interesting is these things rotate very accurately. Even the Earth rotates very accurately, but it has jitters. You would have heard about it, that even the definition of the duration of a day can change a little bit. There's a jerk in the rotation of the Earth. These things are rotating very, very accurately. If anything disturbs that rotation, then you can pick it up, because your ability to measure these pulses, we can measure them nowadays to 100 nanosecond accuracy. So you say, wait a minute, how can you measure a phenomena at 100 nanosecond? So this is this is where all the technology and the ability to pick up these signals and characterize them that to the level. Now you say, is this signal going to deviate a little bit, even by a few microseconds? I will be able to pick up that change. I can ask what can cause this signal to deviate. So when a gravitational wave passes, it actually causes a dilation in what is called the space-time. So effectively, the distance between us and the star shortens and increases. Okay, it's like when the crust and trough of a wave goes by in any such motion, there is so when that changes, the time taken for the pulse to travel will change by a small amount. So the pulse came here, the next one instead of coming here, the expected time will come a little bit early, next one a bit more early, and then again it will slowly go back, and it may even go the other way when it goes to further. And those changes are of the order of microseconds on time scales of weeks to months as the gravitation. So you say, can you pick this up? If you can pick it up, then you can infer the passage of a gravitational wave. Okay, and this result just came out last year. So you say, how do you do this? So you monitor a bunch of these fellows in the sky, because there are also there are some intrinsic jitters also that happen, and some are produced by the irregular medium in our galaxy, because the waves have to travel through that, thinking that disturbs the propagation, can cause an apparent change. So you have to monitor a bunch of these in the sky, and then combine the signal in a manner in which you can then infer that, look, there is a evidence for a gravitational wave that has passed by. And so this result came out just last year. We were part of an international effort where different observatories were monitoring a bunch of these pulsars for a few years. So this experiment is painstakingly done over a few years, and then you're analyzing data to see minor ripples in this arrival time of these pulsars at microsecond level accuracy. And the first publication that came out now show a tentative detection of a gravitational wave signal in this, which with few more years of data, one should be able to build it up and show very clearly the presence of gravitational waves passing. Then they would ask, can you detect one particular gravitational wave event, that some two big black holes coalesce somewhere in the universe, produced a ripple, gravitational wave ripple, and that is going by, can you pick it up? So, these are some of the kinds of things that we have produced. We have detected some very far away radio galaxies in the universe. So there are, in different areas there are different kinds of results that have come from the GMRT.
Is it GMRT open for visitors like all?
Yes, definitely. So what happens? The way we work is that there is Fridays is the visitors' day,
Okay.
and there's an actual sign up online form. But that is usually taken by schools, colleges, big groups, 50 to 100 people. So we allow two groups, one in the morning, one in the afternoon, and then there's actually a duty roster where our team members show the people around, and so that's a formal visit. For smaller groups, then we do it via individuals, that somebody like me or somebody would say, I have some visitors coming. Small group of 10, 15 people, and then I will be taking care of showing them around, and then we get the permission. So there are these two ways of visiting, and you're welcome for either one of those.
I think we know you, so we'll
Yeah, definitely.
go with that. Definitely.
One last question, and then
Yeah, last
we
question.
close the formal session.
Yeah, no, thanks a lot for the sessions that brought back memories of this program called Cosmos by Carl Sagan from my childhood.
Cosmos,
Yeah,
We always
I used to love watching it.
We'll interest us in continuing
Yeah.
that.
So, one question, Jen, with this advent of all this, mobile penetration, Wi-Fi and everything, how does it impact these, how does it impact?
The biggest is our biggest enemy.
That's what I've read in
So
general,
just
but-
when was it? Day before yesterday, I was in Delhi sitting with Secretary Department of Technology, meeting with Airtel, Idea Vodafone. Can you please contain the mobile transmissions around GMRT? Biggest problem. Yes.
Interferes.
See, I think optical telescopes and the remote, mountains, everything just to avoid the city lights. But this is like the penetration of mobile, everything is so vast.
Yeah. So I didn't go into all those. That our the biggest challenge to our own curiosity is our own activities, so to speak. And obviously, society has to prosper and grow. So when GMRT was set up and conceived in 1980s, there was no mobiles. Okay? And that area that was chosen was reasonably,
Secure.
you would even use the term backward or whatever you want to use it. Okay, it has now grown. It's a thriving, with the sugarcane cultivation, grapes, and everything. It is a thriving area, and so anything that emits radiation, no matter how weak, is a problem. So when you switch on your car and the spark plug sparks, you can pick it up. Okay. So the Indian Air Force Sukhoi plane, when it taxis on the Pune airport, we can pick it up. And when it flies, then we have to stop the observations in those frequencies. So things that you would not imagine that can cause trouble. So we talk about that living under high tension lines can be a health hazard. Okay, so you say why? So all high tension power lines have a coronal discharge, a certain amount of electromagnetic radiation that they are putting out. We need to keep these lines at least 20-25 kilometers away from GMRT. So, and there's a constant need. There are, power is generated in the central parts of Maharashtra. It has to go to power hungry Bombay. Those lines go right near the GMRT observatory. And it's a constant this thing. Can you please move this line 15 kilometers further north and it is crossing? So windmills. So there was people who wanted to set up windmills, and windmills produce huge amount of electromagnetic radiation at our standard. So again, when those people came, we had to work with them, get them shifted to a distance which is at least 20-25 kilometers away. There is, I think I should not talk too much about it. There is a proposed Pune-Nasik high-speed rail line. Some of you may have seen or heard about it. The original route was going right through our GMRT array. And electric line means what? The pantograph, when it runs against sparks. Anything that sparks. So our constant thing with Maharashtra Electricity Board. So you know that if you go anywhere, the transformer, there's a fuse link for every transformer. In your house, nowadays you have MCBs, but in old houses you have those fuse links. If you don't put the fuse link properly, it will have a micro spark. That's how they heat up and burn also sometimes. Any of those is a problem. So we used to go to them, and in the rural areas we go, you will see that the way they put yes, it's a wire with a stone which acts as the force to hold it in place as compared to a proper plug-in fuse. That thing, when the wind comes, it does this sparking. Even the line, when they join the line to make a line, the conductors, if you don't do it properly, there is always some micro sparking. And then we used to go and tell them, see that joint, what is wrong with this joint? There's nothing wrong. He said, no, this is what it is doing. Can you please improve this joint? So that's so the new telescopes that I did talk about, the square kilometer array, they are being built in semi-desert regions. Okay, like in Western Australia, right at the edge of the Great Australian Desert on the western side. Such that you can still take infrastructure there. And you have to get power, signal, human beings to go there and do the things, but you make it as remote as possible. It's just like some of the optical telescopes go to the Himalayas. That is for a different reason. It's to get the height, so that the atmosphere, lower atmosphere that corrupts the signal, you are above that. It's just like going to an altitude airplane for doing this. But one has to do all these things. And then again, so you say you can't avoid all of it. Then we have to improve the electronics that we build to be tolerant to the noise, filters, and dynamic range of the system, so that when these bright signals come, it does not get saturated or spoiled in its performance. So a lot of that happens. Even our own equipment. So if you come to GMRT, you will find we can't use air conditioner like this. It has a microprocessor inside. That microprocessor radiates. So we take out the electronics from the air conditioner, put it inside a Faraday cage. So a Faraday cage is a metal box that's completely sealed, so that no radiation can escape from it. And then we put it next to the, because you cannot live without air conditioning. You cannot live
What
without
you're saying
laptops.
is all the people in your staff are not mobile addicts, right?
Mobiles are not allowed.
Yeah, that's what I'm
when I
saying.
enter the
So I
observatory,
think it's a good thing, then.
so if you want a mobile detox, come stay there overnight. You will get an immediate natural mobile detox.
Just before there's a question
Okay.
on the online streaming. So Yogesh asks, as an individual who is not an astronomy professional, how can one contribute to serious astronomy?
That's a very good question. It depends on what stage of life you are in. If you are a student, then but there are citizen science groups. So if you are a regular citizen, if you're a student, you can still chart your career depending on how you want to go. But if you are already in some profession but are interested, then there are citizen science groups which, depending on your level of interest and expertise, allow you to at least learn about things, even dabble with some data, and even some of them have produced some useful science also.
IVE also already has some groups, something like that.
Those are
Associated groups.
Outreach teams, but but there are the associates of IVE are also professionals in either somebody in some university or some college. What that program of IVE does is, let's say you are a physics professor in some college, university, and you would like to get into astronomy, then they give you an opportunity to learn and grow and get associated with that kind of design. This one that I'm talking about is more citizen science groups, and I can, if you ask him to just send me a message, either by email or whatever, I can put him in touch with some citizen science groups which provide an avenue for people to do that. There are also, in optical astronomy, it's easier to have hobby kits where you can make your own telescope and do simple things. In radio astronomy, it's a bit more challenging because the signals are much weaker and it's harder to build something which can show you some decent quality of signal. But there are some sort of equivalent of hobby kits in radio astronomy also, which they can try to assemble themselves and use them for simple experiments.
Anything else? I think it was a power-packed session. I think every second line he said had so much of meta content that we can dig deeper into it and continue forever. Personally, I was thoroughly engaged, but I think we have to call it a stop now. People are also online as well. So thank you so much for this, taking us through the universe of a session, pun intended. I think so many different levels of takeaways in terms of taxonomy, structure of things, how things are attempted, accidentally discovered, and taken forward. So thank you so much for this amazing session. Little thank you note from our side before you leave.